Hey, and welcome to another Day's Treasures video. And this time we're going to talk about circular linked lists, but let's start out with a linked list first. Now, linked lists are generally thought of as a linear sequence of data, and so that means that there is some beginning and there's some end. Well, there's a lot of applications where we can actually think of linked lists in a cyclic order, meaning there is no beginning or end. So we're just kind of repeating a pattern of going through the data and then starting over. Okay, once we reach the end, we go right back to the beginning. And one of those, an example of this would be a typical multiplayer turn-based game. So here we have six players. The first player, it's his turn. So he's up. He performs whatever actions he needs to on his turn, and then when he's done, he's kind of put at the back at the end of the line. And so then the next five players, everybody else is waiting to take their turn. And so by the time the next five players are done, then it's player one's turn again, and it just kind of repeats this process until somebody's won, right? Okay, so a circular linked list is really just a singly linked list where the tail references the head. In a singly linked list, the tail references null, meaning that it ends. And like I said, this is a cyclic order, so it doesn't end. So we just have the tail, just shown in this diagram. The tail's next reference just knows where the head is. Okay. So there's a couple things about this first before we move on. Is there's going to be a new operation that we're going to be adding into this, and that's called rotate. And all that is we're rotating the head node to the end. That's it, and it's actually really simple. And I'll show you next how simple it is. But and then the other one is we're actually going to make an optimization to where instead of referencing the head and the tail nodes, we only need to know about the tail node, because the head is always the tail's next reference. Always in a circular linked list, it's always the tail's next reference. So we don't actually need to know. We don't need to have a specific reference point for the head because we always know where it's at. And this actually makes the code simpler. And even if you don't care about the new rotate method, so you just want to use a circular linked list, it's actually more optimized to use than just a typical singular or singly linked list. All right, so we're going to look at the rotate method real quick. Like I said, this is very simple. So here we have four nodes. We know we have a reference for the tail node, and I just kind of have the head there just for showing you the purpose of where it should be, but we're not actually going to explicitly worry about it in the code. So whenever we want to rotate, meaning we're going to bring the element that has a value of 5, that's going to be the new tail because we're taking it to the end. We're bringing it to the end. All we have to do is say tail equals tail.getNext. So basically we're saying tail equals head, all right? And yeah, that's basically what we're saying, just tail equals head, and that's all we need to do. We don't have to do anything with the head reference because we don't care about it. We implicitly know where it's at without actually defining it in the code, okay? And that makes this rotate so simple. And for the next operation I want to talk about is adding when we want to add a node into the beginning of the list. So how this is done is we take a new node, we're going to pass in some value we want it to hold, and we just set its next reference to the head, or we're going to say tail.getNext. All right, because we know the tail's next reference node is the head implicitly. So once we do that, then we just set, hey, now the tail's next reference, instead of being the head, we want to set it to the newest node. And then we increment the size field. Okay. So real quick again, we have this new node. We're creating a new node and setting its next reference to the tail's next reference, which was the head. And then we're saying now the tail's next reference should equal to this new node. That's it. Okay. I'll explain a little bit more when we code this. But oh, and real quick, you might be one. I'm not going to go over adding to the last because it's actually very simple. We've actually done the hard part right now. When we want to add last, all we're actually going to do is make a call to this algorithm, and then we're gonna then we're gonna say tail. Then we're just gonna set the tail equals like tail.get next. Okay, so last thing I want to talk about is the big O notation. All right. So again, real quick, big O notation is what is the time? What is the time to perform the algorithm as the size of the input increases? So I don't like talking about the best case because that hardly ever happens anyway. So don't care about that. So we're going to talk about average and worst case time complexity, and then space complexity. So on average, let's talk about the access and searching first. So accessing is the same as indexing. You might see it interchangeably called accessing, and linked lists don't index. Arrays do. Okay, so like if you want to say array of index of 5, you can go right to it. It's a constant time to access that part of memory because it's indexed. Linked lists are not. You still have to traverse through the linked list to find whatever it is. It's basically the same as searching. Okay, and these are big O of n because if you have a size of 10 or if you have a size of 100,000, the time to search for whatever value that is, because we don't know where it's at, we have to traverse the list, is going to proportionally increase with the size of the input. So the time is going to increase linearly with the size of the input. And we call this big O of n because that it's linear time, right? So n is the size of the input, so the time is going to increase alongside of n, all right? So it's just big O of n. Insertion and deletion are next. So insertion is big O of 1 for whenever we're inserting into the beginning or the end. If we're inserting into the middle, then it's actually still big O of n because even if you traverse to the node that you eventually find, so you're search for it, which is big O of n, right? But generally speaking, when we're speaking of time complexity, it's just to perform the operation. So if you know where the node is, then we're only worried about how long does it take to perform the actual operation of inserting. All right. So even if we find the node in a circularly linked list, again, this is still a singly linked list. There's no the underlying implementation is singly linked list, not doubly. Okay. So we have no previous reference to know where the node before it is. So even when we find the node and have to perform the insertion somewhere in the middle, we still have to actually traverse from the head to whatever node is before it in order to manipulate the references. Okay, in linked list, you're really just manipulating references. So to insert somewhere in the middle, you still have to do a search, which is big O of n. So inserting anywhere besides the beginning and the end is big O of n. All right. Now deletion is only big O of 1 when you're inserting into the beginning, because if you're inserting into the tail, we don't know what the previous reference, we don't know the previous node before the tail, right? Because we have no reference point to it unless we traverse all the way through the list n-1 times to get there. So deletion is big O of 1 if we're deleting from the beginning, big O of n anywhere else, basically, okay? And it's the same for the average and worst are the same for circular linked lists, right? There's no difference. Because the worst case, you have to still traverse the whole list, and that's just big O of n. So no difference there. And space complexity is big O of n. And so again, space complexity, real quick, is just how much storage is used to perform the algorithm or to do an operation on it. And we don't need any more space besides the circular linked list that we have. We don't need any more storage space. So whatever the size of the linked list is, which is n, that's the size of the input, that's all the space we need. So hence space complexity is big O of n. All right. So I hope you learned something, and I'll see you next time.